Heat degrades electronic performance and reduces reliability, and is the single biggest factor in field failures. Simcenter Flotherm XT connects MCAD and ECAD workflows to significantly shorten the thermal design process. Designing and validating a board's power delivery network to meet impedance goals is also a major design factor. Not enough voltage getting to ICs from power supplies leads to IC malfunction. Excessive current densities cause heating that can reduce component lifespan and even damage the PCB. To achieve the most accurate IC temperature prediction, the heating due to the current routed through the PCB must be included in the thermal analysis. To achieve the most accurate prediction of DC voltage drop in current density and the resulting joule heating, accurate PCB temperatures are needed. Simcenter Flotherm XT and HyperLynx Power Integrity co-simulation provides a streamlined process for connecting these separate but dependent design disciplines. During the Simcenter Flotherm XT simulation, PCB temperatures are provided to HyperLynx Power Integrity for a DC drop analysis. HyperLynx Power Integrity returns a calculated joule heating that is mapped onto the PCB in Simcenter Flotherm XT. To illustrate the speed of the DC drop calculation, which is performed during the co-simulation, we will briefly introduce HyperLynx Power Integrity, or HyperLynx PI. We have the PCB that will be used in the co-simulation loaded and will run a DC drop simulation. For the co-simulation demonstration, we will power 2 nets, but simulate only one here as an example. I can choose to export the power map file, a result from the DC drop analysis, for Flotherm if rather than a co-simulation I want to import a single power map to be used in the Simcenter Flotherm XT analysis. While not as accurate, it does provide another method to include board heating in a system-level thermal design. I'll perform the DC drop calculation on the selected net. The simulation runs in seconds and provides a report as well as a graphical display of results such as the DC drop voltage and current density. To link this electrical simulation model with the Simcenter Flotherm XT thermal simulation, I will export the design archive, which contains all the files needed for the co-simulation. Shortly, we will see how I link these files in Simcenter Flotherm XT. In Simcenter Flotherm XT, I have a model loaded, which consists of a tabletop, case enclosure, and an axial fan. Simcenter Flotherm XT EDA Bridge is used to import the board layout. This application supports several different file types from EDA tools such as CCE, IPC 2581, and ODB++, and these can be set up as needed before transfer to the project. During this process, it is possible to save the progress and create a file with the extension EDA Bridge. This contains information relating to changes the user has made, and it is possible to open this file format in EDA Bridge. After importing the EDA Bridge file, I import the thermal list, which contains power dissipation, component temperature limits, component model definition, and thermal model ID. The thermal model ID is a reference label that we can use to swap with thermal models of the component stored in the library. We can also swap with library items using part name or number, but the thermal model ID recognizes that components with different part numbers, for example from different manufacturers, have the same thermal characteristics. Now that we have swapped in our component library parts, we will transfer the PCB to the simulation project. There are a few board modeling levels supported, but for co-simulation, the material map option is used, which models the board as a network assembly. The material map represents the board as a resistor, capacitor, or RC network. It allows Simcenter Flotherm XT to model boards in detail without the expense of excessive computational mesh. Once the board is transferred to the simulation model, it is aligned to the standoffs. The co-simulation and material map settings are accessed in the PCB property sheet. First, I will change the via material to a solder alloy. To control the number of nodes in the RC network, the method to process the board can be set to either fine or averaging. The fine setting is the most accurate and creates extremely fine detail of traces, vias, and plating thickness. Averaging uses the resolution setting to subdivide the board into tiles of effective properties. The averaging method is used here with a resolution of 100 for about 172,000 total nodes. Power map files that are created in HyperLynx PI can be imported and will assign power to the appropriate nodes in the material map. While less accurate than the co-simulation, it provides another method to easily include the power dissipation from the DC drop analysis. To set up the HyperLynx PI co-simulation, we navigate to the archive folder we exported from HyperLynx PI and select the CCE file. Next, we choose the electrical nets to include in the co-simulation. For this analysis, we choose 2 nets. The model is now ready to solve. HyperLynx PI DC drop analysis is performed at each Simcenter Flotherm XT solver iteration. The co-simulation was performed in a 3D CFD conjugate heat transfer model and can be easily implemented as part of a thermal and power delivery network design for electronics products. To view the properties and results within the material map, the property sheet is opened. We will view plane 6, which includes a significant portion of one of the nets we included in the co-simulation. Here we see the thermal conductivity in the Y direction. Even with the resolution of 100, the copper distribution is represented. The plotted temperature shows the temperature rise due to the board heating from the co-simulation. With Simcenter Flotherm XT and HyperLynx PI co-simulation, the predictive accuracy for thermal and power delivery increased significantly and is easily implemented.